Okay, welcome to this new module. It's on why Mathematica, if you want to learn to code, why Mathematica and not Python? Or what is computing and code about? Also, why and not, for example, Python? So, again, I don't want to make a simple answer to that. It will take some time and a little concentration, but I think it's worth it. So the principal distinction I would say is Python as Java is as a summary is imperative programming language. And this means that you say how to do things, and with that you are in time, at night, with the engines and the production, and you're performative, and you're with a satire. Whereas Mathematica, in the tradition of Lisp, that's a declarative, so-called declarative programming language, and there are only these two, imperative and declarative. And this plays at day. It's not like Python, a kind of instruction manual, but it's towards poetics. And it says not how to do things, but it questions what to do with computers. So and I would even say, so if we ask what are computing and code about, that computing is the athletic thing of computers, so this is at night, it's a production. The articulation and the intellect of computers, this I think is with code and with applications. So that's for a summary, so what you can expect. So we as architect, therefore, I would say we should prefer to the declarative, and therefore I suggest to learn Mathematica, the poetic way of coding. So to start what we had, our argumentation. So if this is a line of time, and this is cause and effect, reason, and so on, then there is an obstacle. So we said that in the time, this obstacle, so we are blocked here. For example, in the scale of but, there is a way to go around. So, and we talked about this as time, and this, for example, as space. And the other way around, or you can go here. So, for example, we had this discussion on a circle and a line, and we discussed it with in the rational number plane, and we had seen that in rational number plane you only can get points, certain directions of your view. So this is the line as in time, and this is in space, and you only can see points of space, and the difference of these points, this is your intellectuality of space in the rational number plane. So then we said, as we had it with if this is 1, then this is irrational. So we talked with that as time, and this as space. And then we said this is irrational, and this is square root of 2, and we symbolized that. If this is with numbers and this is with numbers, this is with the symbolization of it. So we got this idea that these numbers here, they are of the rational number plane, for example. And then we say if we go and work here, this is the irrational number plane. So, and we got a new kind of ratio, and this is the real one. So, and then we've seen that with this real number plane, we are able to articulate this circle, and then we can find an intersection between in the scale and the real scale of space. We can't get an intersection with the rational scale of space and its geometry and its number. So therefore we can say there is an obstacle, whatever it is, it's in the rational number, but if you go one step in more abstraction, you can go around with the real numbers and go there. So for example, we have these electromagnetism today. So we can, for example, say in the rational number space, we have a drop falling in water and getting the drop and taking space like these waves. And then we have this obstacle. But you see with this electromagnetism and with the antenna, which is in this case now it's in complex number space, but this is able, you see it's similar, it's waves and time and space, electromagnetism. So it's electro, which is a particle, and magnetism is a wave, time and space and time, particle and wave. So therefore with electromagnetism, for example, with our mobile phones, we can go around. So we can talk here with a person on the other side of the world with electromagnetism. If we shift to another scale of space, we just go around the obstacle. So we talked about that the window is something like that, for example, or a door. So, therefore, we want to get the nature of how to domesticate these way arounds. So we also talked, therefore we had this kind of helix. We had this abstraction of space, S1, S2, S3. And this is our quantum space. It's a space of Renaissance. And this is a space of antique Greek, for example. There's some numbers. So we had then the rational numbers here. We had the real numbers here, and we have the complex numbers here. So we said this is night. It's a metaphor, and this is day. And so, question now is, if we are in our quantum space, this is today. And we don't know what is going on. So it's bright day, we go out of from the last night, we go out of our cozy home, and we don't know what to do. Everything is alienating in bright sunlight and quantum space. So we had the classical mechanic here and so on. So there are two points of stability we can learn on, and there are two different movements in thinking about that. So the first is the movement towards the last day. This is A. And this here is the last night. So when we say with A, we call that abstract from the last day. It's an abstraction, these things. So you're in the same constellation. If we think all this as a planetary system, we're in the same constellation, but in another scale. So B is the inverse constellation. So we can say that is an inversion from the last night. So we introduce these two concepts, abstraction and inversion, to learn what is going on. So, and of course you can go and reflect here and can make, so, but this is the first step of getting stability in these kind of things. So what we've seen here, this here is not like the antenna. It's electromagnetism, this is complex, and the wave is rational. As we said, rational is not the complex. So this is abstraction. Good. Having that, okay, in the next step we want to see how technically we want to go from day to night and from night to day on with an electromagnetic device. How, and therefore we ask the technical question how to go from the reality of, for example, the rational to the complex number plane, to go around and then go back. So how to go to this number plane, this is number 1, and then go back, this is number 2. So this is from how to go from a day to night. So this is called analog. This is from the day. Digital, this is from the night. Converter. So, and it works like this. So you have a signal at day. You're measuring, for example, temperature or the density of sound, the density of sound, or you measure the intensity of light, or whatever you do. There are thousands. Everything you're doing, it's all the sensors and all parameters we have can be converted to electromagnetic, to a certain currency. If you have this is ground 0 volt, this for example is 5 volt, then we say this, for example, the measurement, this is the analog signal, is 3.2 volt. So this is going to a converter and asking, is this smaller than another signal? And this is artificial. This is a generator, and this has 0 volt, this is 5 volts, and this goes up and down and up and down, and for example we take 1 second. De facto it's extremely fast. So which means if this A is smaller than this jigsaw, then the result is 1. Otherwise it's 0. So this goes to another thing. So here we say it's a plus, and this says if both of them are plus, then go for plus, otherwise go 0. And we feed it with another generator. And we have here O, and here we have here 1. And this generator simply goes in very high frequency up and down. And we put that in here. Which means if there's a 1 here and A is smaller than this oscillator, then this is a 1, then it gives a 1. If there's a 0, then it's a 0. If it's the second one and it's smaller than this oscillator, then it's another impulse. So then we simply have to counter, and this has, for example, 8 bits. 8 bits. So therefore we count and we give a number. So this means if this is 3.2 volt, if we have 8-bit 256, then we are about 165 as a number coming out. So we need then a certain resolution, so we need have to calibrate the frequency of this with the second so that we can count 250, so it has to be 1 by 250 if this is 1 second to be able to count 256 for 5 volts. That's it. That's a digital analog converter. So what it is doing, so simple principle. So what we are doing we are laying out an analog, and this is digital. So what we are doing is we have a certain intensity, an analog intensity, and we are laying it out in time, directly. We are projecting it in time. So it gets a certain number in time. So therefore we have, this is a technical implementation of the stereographic projection. And this is an electromagnetic implementation of, for example, this stepping wheel of the calculating machine of Leibniz, or here a Babbage differential engine or analytical engine of Babbage, 19th century, 17th century. So it's directly like what we said with time. So if we want to look at it, this is a unity of 256. So we have 256 points. 256 is a unity. And then we are counting 165 here. So it's an angle. We count angles, and this is like numbers. It's an electromagnetic implementation of an analog intensity of space projected to a number in time. That's it. And it's the same like calculation. So the other way around, the analog converter. So this is how to go from time to space. This is one. This is analog digital, and this is digital analog. This is very simple. We simply have to get a certain time, and we fill, for example, a pixel of a screen. We simply fill it with elements, and then we so that's for example an LED, and we have for example a frequency of 100 hertz, and then we fill it with electrons, and then it emits photons, red light, green light, blue light, and so on. So these are our grids our electric grids, and then of a certain intensity, and so on. We just fill it empty, fill it with electrons empty, so we are just filling it up. That's the digital analog converter. Again, we need a certain time, and then we unroll it and put it to the vertical, to the intensity of a certain location. That's the digital analog converter, which is here. So if we want to speak, we have a microphone. The microphone converts it with the analog digital converter. Then we are in the electromagnetic, so we are here. Then we send it in the electromagnetic domain, and we bring it back to the speaker in a corresponding way, and then we hear it on the other side of the world. And then our planet is the obstacle. This is how to go from day to night and from night to day. And we can do it with all physical parameters we know, because we have sensors and actuators for all physical parameters we know, nearly. So there are thousands of them. So that's the second chapter. If we have this, people always say there are, with the data, for example, there are traces of that. So we can trace it, and there's always a reason for it, and so on. You see, with this notion of the obstacle and so on, is exactly not the case. So, and what we have on a technical level, I can show you here. It's so what we said now here, how to abstract from space, go to the time domain, and go with electromagnetism and go back to the others around the obstacle. So we're abstracting from ground. We go from logic to logistics. So in the actual technical facticity we have, this is how our technologies are organized. We have, it's a so-called OSI model. And here we see we have 7 different layers, how all the industries around information technology are organizing themselves in levels of these kind of abstraction. So it's 7 of these abstraction, how they organize themselves. So and we distinguish between media layers and host layers. So then we have the physical layer, which is what I explained. Then we have a data link layer, we have a network layer, we have a transportation layer, we have a session layer, we have a presentation layer, and we have an application layer. And they all abstract, and you can change technology in between. So this, for example, we have here. This is with go here. This, for example, is Baran, 1964. We have here how to digital networks composed of mixture of links. So all this internet is military technology. Everything is mixed. So you can cut any cable; it's still working. So the transmission of of data of your mail or even of your phone call it's not a straight line. So you cut it in on a certain OSI level, you cut it in a lot of different small parts of bits, chunks of bits with addresses, and then they spread across the world to all the networks that take the most comfortable way they find with their own navigation system a way, and then they go to the receiver, and then they are recombined. And after recombination, then you get the results. So all this is very fast, but it's like that. It's a burst of fragments into a networked system, and it doesn't matter if there are holes or misconnections or repairs or crashes and so on. They just find their way, and they are reconfigured at the destination, and then you get the result. So it's a complete abstraction of the reality of time. So it's a logistics in geometry how this works. This is very important, and it always somehow works like this. How to get and to switch between different levels back and forth. Good. So. Let's go here. Our question was, what is computing and what is code? So then I would say here, the last day, or it's a memory of the last day. Of the last day, and this is the last night. So this is ichnographia. This is orthographia. So and this is the new day. Is Sino. So, therefore, we invert the ichnographia, and we abstract the orthographia. So, if you go to the trivium and to the way how the modes of talking, it's like Doric, Ionic, and Corinthic. Then this is the tragedy. This is the satiric, and this is a comedy. So, therefore, so start with this. So therefore we go in inversion to this, and we go in abstraction to the tragedy. And to get out of the tragedy and abstraction for that, you have to make jokes. And you have to make it serious what is done with the satire. So now go for a set of conceptions so we want to go with the inversion here and the abstraction. And we want to think and give it a rich body we can think about. So it corresponds to this spiral. So all the conceptions are constant here. Also, so we can keep, for example, architecture is here, engineering is here. So we can learn from here in abstraction what architecture is. And we are inverse to engineering because engineering is at night. Now I will give you a lot of so this is night and this is the day. So this is time. We call that here the space. We called this here numbers. We use numbers, and we use here characters. So this is with calculation, and this is with writing. So then we had the rationality of the unity of space towards the angle, towards the linearity of time, and we have the angle we can trust. Here it's just the other way around, and this is the area. We discussed that. We can learn by the area, and we can learn by the angle. We call that the real, or reality, and that's the ratio. So we had the earth and the four elements and the water here, and we had the air and the fire here. We had arithmetics and topology. Here we had geometry here. So then, for example, we said our sensories, we discussed the things with on a technical level. We have the eye of space here. So this is our nature, this is the circularity with the eye, there's the sensor, and so we had the stereo, graphic, we had the perspective here. Eyes of space, and the actuatory is, this is the hands of time. And the other way around, we have the ear of time. So this is our sensors of the day, of space as the ear of time. And we have the tongue, so the talking of space. And this always goes around. Stereographic projecting, or with the Vitruvian Man, with the square, and with the circle, the circular nature. So this here, like here, circular nature, and the linear nature of a day. So the linearity and the circularity. So we have the navel interesting here with the Vitruvian Man, and we have the gender or the sex here. So go further. We have the engine, so which is driven by internal energy. You have to fuel it, and here it's the machine or the motor. And this is a machine, like a windmill. This needs external forces in space. Very important distinction. So therefore we have the production hall, production in time. It's circulating and putting things like here, like our converter. It's producing artifacts, and we have the artifacts here. So therefore we have engineering here. And we have architecture here. And I would say in strong contrast, design is here, interestingly. We have structure. Design is a kind of interface engineering. Or you're with the construction of, and you're with the machines, how to do things and so on. You're not with the artifact, with the architecture. So we have a structure here, and we have form or figure here. You have the sign here. So you assign, signature and assignment. So you point a certain things directly. Whereas here it's a symbol. So, and so on and so on. I think we have the urban, the infrastructures with here, and here I would say we have the city. Whatever it is to discussion. Currently have a crisis of the city. Good. Having this list. So we know all this is constituent, and this is the nature of. So this is so we have to embody these to rethink these conceptions. So this is our nature, and this is our desire. Yeah. So. In programming languages, to come to our question, why mathematica instead of Python, for example, we distinguish between imperative and declarative programming languages. So they say how to do things, and they say what to do. So we have here von Neumann, and this is Alonzo Church. 9341936. So this is Java or Python today, and this is Lisp or Mathematica today. So I'm not, it's a kind of coincidence that it's called Mathematica, and we are talking about mathematics this much and so on. So it's by accident. Now I want to give you an example how to add. Go Java, how to add two numbers. Ask, for example, this. Beginner's book, and here you see the first example. So the first is, you see how this is done. Yeah? So what you have to do is add two numbers. You have to, this is just create a function, you have to say, and therefore you have to put it step by step. You have to make this machine step by step. So you say, of type integer, there is a variable, and we assign to this variable 5. There's another variable of integer, and we assign to it number 5. And then we make another, define another variable, and we assign that to variable, and we say this should be of integer. And then we say the addition of the first integer with the second integer is the sum, and then we print it and put it to the output stream. So you see, it's as we have it here, it's a layout. It's like here. So this is what we think computing is. If, then, bam, 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 and it's a production line of things. So this is how Java works. So it's a production line, the first thing, and if you look it up, you see a solution for a problem. So if we go, on the other hand, for Mathematica, reference, you see, do basic calculations. They unfortunately say how to, I say what. But the first thing is, you simply have to write 3 plus 4, and then it's there. So it's just middle out. You just start, bam. It's more, it's not like here, step by step with Java and Python. You have to define a problem, then you get all your elements, and then you put your elements in a certain structure, and you put the result and present the result. It's just like throwing a drop in water. Just 3 plus 4, bam. And he thinks, you simply say what you want to do, not how these things should be done. That's the first thing. This is a very important difference. And the second thing is, what you see here, it's not an instruction, it's a lexicon or an encyclopedia. It just says what you can do with numbers, how to do calculation. It's not about, there's no problem. They simply say what you can do with all this. It's a collection of things to do. And I think that's very, so we have here an instruction. And here we have a lexicon. And here we have a problem, solution. Here we have a bunch of things to get ideas. Yeah? I think this is enough for you as architects there in this kind of discussion on this topic. Now go for the next chapter. Having all this, now we say this is our planet. What does it, which side is architecture? So I said already, I think it's here. Now I want to link it again to Alberti, and I want to link our discussions here. So then it's of course, then Lisp and Mathematica, the lexicon, a bunch of things in this architecture, and all these things. And Java, the instructions, problem solving instructions. Python is with engineering and with design. So now I want to bind it back to what we said with Alberti. So we have a point in time. We grow an urban environment. So, and we had this branching. So to cover an area, we had that with a stereoscopic projection. So we first have the planet. currently we are interested in the climate or the environment. This is what we're currently discussing. So then, second, this is the urban. And Alberti says this is an area or region. We would say this is an urban region. So, and this is about, I would say, in contrast to climate, it's health. So, I would say, this is what we see here. It's flat on the ground. This is at night. This is day. So we have the infrastructures. We had structures here. Engineering structures, engineering, design, production, engines, motor, infrastructures. This is what we observe in the urban here. And that's the logic of the night. So, with architecture and Alberti, we said we have to go. So this is always horizontal and spreading. The logic of the night with all the infrastructure. So here we are on time, branching. And bounds. So, at the day, we'd call that I want to be a tree. So I take all these infrastructures and I grow towards the air. So this was the earth, and this is ground and infrastructure, and this is the air. So we said that I want to be a tree, or I want to be a piece of architecture, I want to be a building. So we said it's zero-dimensional, one-dimensional, it's vertical, so we have to leave the domain of night, go vertical with a column, and then we build our structure, 1, 2, 3-dimensional building. So that's a building. So, and we said with Ishigami, this is climate again. Today. So we have a strong correlation here. And this is what we have in our discussions. In the discussions of architecture today, we have a strong correlation. So the building is a miniature of the planet, and it's logistic of the day. That's very important in contrast to day and night. So we have the logic here, the logic of the night. It's a logistics of the day. So logic means here in the night, and if you go around, you simply have to make an address, a phone number, and then you're somewhere else. So this is what we discussed. So that's the logistic. So it has no traces. We had the OSI model with all the different layers of abstraction, and there's no trace. We discussed it. So that's logistic in contrast to logic. So we have this correlation, and then we have the human here. That's a human. And I would say with all these sports and trekking, hiking, and with all this vegan food, and we are about health, very dominantly about health again. So, and that's in strong correlation to the urban, as we can observe with Alberti. So this is not our invention, it's just what we've seen here with Alberti, and we can abstract from that to our today's scale of space. But the mechanics here stays the same, and it stays the same to Vitruvius. So this is Alberti, Vitruvius, this is us. So, therefore, if we have this, that's very proper. Go here for this diagram. Yeah, the last night here, this is the urban. This is it right? Yeah, this is the urban. And this is here, the memory of this is the last building, the buildings of the last day. So, and these are the buildings. The memory of the last buildings. So, if we look at all these symmetries here, we can say this here is Python. It's here on the shadow, Eichnographia. And this here is, let's Lisp or mathematica, orthographia. So we need to find something like Lisp in Renaissance. We have to learn in these symmetries. So we need something like mathematica here. And I said these are the drawings. Or this is phonetical writing at S1 with Vitruvius. These are the drawings. They are on this logistical side. That's on the logistical side. That's on the writing. And this is on calculating. So, Python, Mathematica. So, or drawing, was the last day. So, I would say the only difference between thousands of developers in Python and AI is that AI is smoother in doing these things. So therefore I would say this is AI. And I don't make a difference between thousands of computer scientists and AI. So they're just getting more performative in these things. So this is the fertility of our urbanized environment. That's AI. So they take these things here, and this corresponds to the proteins in the human body with Jacques Monod. This is the DNA, and this is big data today. This is the tragedy of the lost world. So this is what we'd seen the last day, the old buildings as big data. So this is what we have, for example, with cultural heritages, and we have with tourism, and we just walk there and look it up and bring it to the digital and get comfortable with that on a symbolic level. So I would say the tragedy of things is big data. They get dead. The data loses any meaning. This is AI. ethnography. This is calculation. These are the processors. And this is, I want to be a tree. This is the new scale of space. And we need a certain writing because we have to talk. So there's another building, and they talk in this way, around the corners. Yeah? And I would say Mathematica is here. Forget this. Drawings, big data, proteins, AI, Python, Mathematica is here on the Scenografia here. So, therefore, this is how to do things. This is a question about what to do. If the how to do is about necessities, this is about contingencies. Then this is about economy, because economy is like farmers working along the lines of necessities, like the settlers at night. And the what is politics. And this was the new settlers. Or this is with the nomads. These are the guys walking around and attacking the old settlements because they're able to go around the obstacles of the farmers and the old settlers. So, and I would say, as an architect, not as an engineer, it's quite clear in this layout that you should focus on this, on the poetics of the new writing, instead of the calculation of the problem solvings and the pragmatics of that. So that's in principle my input for our discussions and my talk. Thank you for listening and see you.